Hello, and welcome to the new episode of The Sleepy Space. Close your eyes and feel the solid ground beneath you. Feel how still it seems, how permanent, how unchanging. But tonight, let your imagination carry you deeper than the surface allows, past the familiar world of soil and roots, beyond the reach of rain and sunlight, down into Earth's most secret chambers where ancient fires wait in patient silence. You are beginning a journey into the heart of our planet, where sleeping giants rest in darkness deeper than any cave you could ever imagine. These are not giants of flesh and bone, but giants made of molten rock and pressurized gas, of temperatures that could melt copper and forces that can move entire mountain ranges. They are the magma chambers that lie beneath volcanoes, and they have been waiting, some for decades, some for thousands of years, for their moment to wake. Picture yourself descending through layers of earth like moving through the pages of an ancient book. The first few miles feel familiar: cool basement rock, water ground flowing through cracks like underground rivers, the steady temperature of a wine cellar. But as you go deeper, something begins to change. The rock grows warmer. The pressure increases with each mile, like diving deeper into an ocean made of stone. At 10 miles down, you enter a realm where the rules of the surface world no longer apply. Here, rock exists at the very edge of melting, held solid only by the immense weight pressing down from above. The temperature reaches nearly 2,000 degrees Fahrenheit, hot enough to melt silver, hot enough to glow like a star if you could somehow see it. Yet it remains solid rock, compressed into crystal structures that exist nowhere else in your daily experience. But deeper still, something magical happens. At 15, 20, sometimes 30 miles below your feet, the balance tips. The heat finally overcomes the pressure's grip, and solid rock begins its transformation into something extraordinary. It doesn't melt all at once, like an ice cube in summer heat. Instead, it melts slowly, selectively, like chocolate warming in your hands. Certain minerals surrender first, the ones rich in silica and aluminum, the ones that will someday become the explosive heart of volcanic eruptions. This is where the sleeping giants truly live, in vast chambers carved from solid rock by their own fiery presence. Imagine underground cathedrals filled not with air and light, but with molten stone that glows with its own inner fire. These magma chambers stretch for miles in some places, containing enough liquid rock to bury entire cities. They are shaped like teardrops or balloons, following the paths of least resistance through Earth's crust, always seeking to rise, always pushing upward toward the surface world you know. The magma itself is not simply melted rock, it is rock transformed into something far more complex and alive. Within these glowing chambers, crystals grow and dissolve like flowers blooming and fading in fast-forward time. Gases bubble through the liquid stone like champagne, carrying with them the essence of deep earth, water vapor from ancient oceans trapped in rock, Carbon dioxide from limestone formations compressed over millions of years. Sulfur compounds that will someday paint volcanic landscapes in brilliant yellows and reds. Temperature and pressure work together here like master sculptors, constantly reshaping the composition of the magma. When the mixture is rich in silica, it becomes thick and viscous, like honey that's been cooling on a winter day. This thick magma traps gases within itself, building pressure like a shaken bottle of soda, storing energy for eruptions that will someday shake the surface world. When the magma is lower in silica, it flows more freely, like warm olive oil, allowing gases to escape gently and promising eruptions that will flow rather than explode. But perhaps the most remarkable thing about these sleeping giants is their patience. Time moves differently in the deep chambers beneath volcanoes. While you live your life in days and seasons, these giants measure time in centuries and millennia. Some magma chambers spend thousands of years slowly cooling and crystallizing, never quite reaching the surface. Others accumulate fresh injections of hot magma from even deeper sources, like underground rivers feeding into hidden lakes. You can think of each magma chamber as Earth's way of dreaming. In the darkness and pressure of the deep crust, our planet processes the raw materials of creation, taking old rock and transforming it into new possibilities. Iron and magnesium dance together in crystal lattices. Silicon and oxygen bond in endless chains that will someday form the backbone of new minerals. Rare elements like lithium and cesium concentrate in the cooling edges of the chamber, waiting to be discovered by future geologists.
The giants are not truly sleeping, though they appear so still from the surface. They are breathing in their own geological way. Fresh magma rises from the mantle below, bringing new heat and new chemistry to the chamber. Older, cooler magma crystallizes along the walls, slowly shrinking the chamber's size while changing its composition. The whole system pulses with a rhythm measured not in heartbeats, but in decades, a slow circulation that mixes and remixes the molten rock like a vast underground ocean with currents measured in centuries. As you rest in the comfort of imagining these deep chambers, consider how they connect to everything you know on the surface. The soil in your garden contains minerals that were once part of ancient magma chambers. The granite in mountains and monuments crystallized slowly in chambers just like these, cooling over millions of years until they became the solid rock we quarry today. Even the water you drink has passed through volcanic systems somewhere in its long journey through Earth's cycles. These sleeping giants beneath our feet are not separate from the world above. They are the foundation of it, the source of the elements that make life possible. In their hot darkness, they hold the future landscapes of Earth, the mountains that will rise, the islands that will emerge from ocean floors, the fertile soils that will nourish plants and trees in centuries to come. The magma chambers pulse with their own slow rhythm, responding to forces we can barely imagine: the gravitational pull of the moon and sun, the gradual cooling of Earth's interior, the slow dance of continents as they drift across the surface. Sometimes these forces align in ways that disturb the sleeping chamber's peaceful rest, and when that happens, the sleeping chamber begins to stir. As you float in your imagination above these glowing underground cathedrals, you might begin to sense the first subtle signs of awakening. A slight increase in temperature, a new batch of magma rising from even deeper sources, the first gentle expansion of rock that has been compressed for millennia. These are the earliest whispers of volcanic activity, the first movements in a dance that might take decades to complete or might begin tomorrow. But before we can understand what happens when these giants truly wake, we must first follow their dreams as they flow in rivers of liquid stone through the deep pathways of Earth's crust. Deep beneath the sleeping giants we visited in darkness, something extraordinary is always moving. While you rest in the comfort of your bed, rivers of liquid stone flow through pathways carved in solid rock, carrying the dreams of deep earth toward the surface world. These are not rivers as you know them. They move without banks of earth, without the sound of rushing water, without the familiar rhythm of currents you might hear by a mountain stream. These are rivers made of molten rock, flowing through channels of their own creation, following paths that have existed for millions of years. Imagine, if you can, what it means for stone to flow like water. Picture the hardest granite countertop or the most solid marble statue. Then imagine it heated until it glows like a sunset, until it moves like thick cream poured from a pitcher. This is magma in motion, rock transformed by heat into something that defies everything your surface experience tells you about how stone should behave. It flows upward through Earth's crust like underground rivers seeking the sea. But instead of seeking the lowest places, these rivers of stone are always climbing, always rising toward the light. The journey begins deep in the magma chambers, where pressure has been building for centuries. Like water finding cracks in a dam, the molten rock discovers weaknesses in the solid crust above, ancient fractures, zones where different types of rock meet and don't quite fit together, places where the crystal structure of solid stone has been stressed beyond its limits. Through these pathways, narrower than hallways, but sometimes stretching for miles, the magma begins its slow ascent. But this is not a simple journey upward. The magma moves through what geologists call dikes and sills, vertical and horizontal pathways through solid rock that form a complex three-dimensional network beneath every volcano. Think of these pathways like the circulatory system in your own body. But instead of blood carrying oxygen and nutrients, these stone arteries carry molten rock enriched with dissolved gases and rare minerals from the deep earth.
As the magma rises, it undergoes constant transformation. The pressure that held certain gases in solution begins to decrease, like opening a bottle of carbonated water very slowly. Water vapor, carbon dioxide, sulfur compounds, and other gases begin to form tiny bubbles within the flowing stone. These bubbles make the magma lighter, more buoyant, encouraging it to rise even faster. The process feeds on itself. The higher the magma rises, the more gases come out of solution, the lighter it becomes, the faster it wants to rise. The temperature of flowing magma is almost beyond imagination. At depths of several miles, it might reach 2,200 degrees Fahrenheit, hot enough to melt copper pennies instantly, hot enough to turn water into steam before it even touches the molten rock. Yet even at these incredible temperatures, the magma flows with the consistency of thick honey or warm tar, held back by its own viscosity and the narrow channels through which it must travel. Different types of magma flow in distinctly different ways, each carrying its own chemical signature from the deep chambers where it formed. Basaltic magma, rich in iron and magnesium, flows relatively freely even as it cools, creating smooth, rope-like textures when it finally reaches the surface. This is the magma that builds shield volcanoes like those in Hawaii, flowing in broad sheets that cool into the dark, fine-grained rock that forms the ocean floor. But when magma is rich in silica, the same element that makes glass, it behaves very differently. This rhyolitic magma flows like cold molasses, thick and resistant to movement. It traps gases within itself more effectively, building pressure as it rises. When this type of magma finally reaches the surface, it often does so explosively, creating the towering eruption columns and ash flows that can change entire landscapes in a matter of hours. As you follow these underground rivers in your imagination, notice how they reshape the very rock through which they flow. The intense heat of the magma bakes the surrounding stone, creating zones of metamorphic rock, stone that has been cooked and transformed without actually melting. Limestone becomes marble in these contact zones. Sandstone transforms into quartzite. Shale develops new crystal structures and becomes slate or schist. The flowing magma acts like an underground kiln, firing pottery made of entire mountainsides. The pathways themselves tell stories written in stone. Some dikes are perfectly straight, following single fractures through uniform rock types. Others twist and turn, following the complex boundaries between different geological formations. Some widen into underground chambers where the magma can pool and cool slowly, forming bodies of igneous rock that will only be revealed millions of years later when erosion strips away the layers above. Time moves strangely in these underground rivers. A single pulse of magma might take months or years to travel from its deep source to the surface, moving just inches per day through the narrower passages. Along the way, it cools gradually, forming crystals that grow like underwater gardens in the flowing stone. Feldspar crystals develop their characteristic rectangular shapes. Quartz forms its six-sided structures. Mica creates tiny mirrors that will someday glint in the sunlight when the rock is finally exposed. The chemistry of the flowing magma changes constantly during its journey upward. Elements separate and concentrate according to their affinities for different crystal structures. The rare earth elements, with names like neodymium and europium, concentrate in the late cooling portions of the magma, creating deposits that will someday be crucial for technologies not yet imagined. Gold and lead follow sulfur compounds through the hottest pathways. Copper and lead find their own preferred routes through the cooling margins of the dikes.
But perhaps the most remarkable aspect of these stone rivers is how they connect the deepest parts of Earth to the surface world you know. Every pebble on a beach, every grain of sand, every crystal in a piece of granite was once part of these flowing streams of molten rock. The atoms in your body, the iron in your blood, the calcium in your bones have passed through these underground rivers countless times during Earth's long history, cycling between the surface and the deep interior in the ground recycling system that keeps our planet alive and changing. Some of these rivers of stone never reach the surface at all. They cool and solidify in their underground channels, becoming the batholiths and plutons that form the roots of mountain ranges. The Sierra Nevada, the coast ranges, the granite domes of national parks, all of these began as flowing magma that cooled slowly in underground chambers and pathways. What we see at the surface today is just the tip of enormous underground icebergs of cooled magma, exposed only after millions of years of erosion have stripped away the rocks that once covered them. As you drift in the comfort of imagining these hidden rivers, consider how they pulse with the heartbeat of the living earth. Each flow of magma carries information from the deep mantle about conditions hundreds of miles below the surface. Scientists can read this information like letters from the interior, learning about temperatures and pressures and chemical compositions that exist in realms we can never visit directly. The flows are not random. They respond to the slow breathing of Earth's interior, to the rise and fall of convection currents in the mantle, to the gradual cooling of our planet over billions of years. Sometimes the flows increase, bringing more heat and material toward the surface. Sometimes they slow, allowing the pathways to cool and seal themselves. But they never stop entirely, these rivers of liquid stone, because they are part of the fundamental process that keeps Earth geologically alive. And as these molten streams make their patient way toward the surface, they carry with them the first whispers of change, subtle signals that something is stirring in the depths, that the pressure is building, that the sleeping giants might soon begin to wake. The rock itself begins to sense these approaching rivers of fire and responds with the faintest tremors, the gentlest vibrations that speak in the ancient language of trembling earth. In the quiet moments before dawn, when the world seems most still, Earth is actually singing, not with voices that your ears can hear, but with vibrations that travel through solid rock faster than sound moves through air. These are the earthquake waves that precede volcanic awakening, Earth's way of clearing its throat before speaking in fire and molten stone. Tonight, let your imagination become sensitive to this hidden music, the seismic symphony that plays constantly beneath your feet, telling stories of pressure and release, of sleeping giants beginning to stir. The language of trembling earth is older than any human tongue, more precise than any written word. It speaks in frequencies measured in cycles per second, in amplitudes measured in fractions of inches, in wave patterns that carry information across entire continents. When magma begins its final approach toward the surface, when those rivers of liquid stone we followed in darkness start to fracture the solid rock above them, they create vibrations that sensitive instruments can detect from thousands of miles away. Imagine the magma chamber deep beneath a volcano beginning to swell like a balloon being slowly inflated. As molten rock accumulates in the chamber, the pressure increases gradually, pushing outward against the solid walls of crystalline rock that have contained it for decades or centuries. At first, the rock holds firm, its crystal structure strong enough to contain the mounting pressure. But rock, for all its apparent permanence, has limits to what it can bear. The first tremors are so gentle they would be imperceptible to you if you stood directly above them. They register as tiny deflections on the most sensitive seismographs, instruments so delicate they can detect ground movements smaller than the width of an atom. These micro-earthquakes, as scientists call them, are like the first drops of rain that herald an approaching storm. Each tiny fracture in the rock releases a pulse of energy that radiates outward through the earth like ripples spreading across a still pond. But unlike ripples on water, earthquake waves travel through solid rock in complex, beautiful patterns. The fastest waves, called P waves for primary, compress and stretch the rock as they pass, like sound waves moving through the air, but traveling through stone at speeds of several miles per second. Close behind them come the S waves, or secondary waves, that move the rock from side to side in undulating motions that would make the ground dance if you could see the movement with your naked eye. As the magma chamber continues to swell and the pressure continues to build, the character of these seismic whispers begins to change. The micro-earthquakes become more frequent, clustering in patterns that reveal the shape and depth of the growing magma body. Scientists who study these patterns have learned to read them like doctors reading the rhythm of a heartbeat, detecting the subtle changes that indicate when a volcanic system is moving from rest toward potential activity. The rock itself begins to respond to the mounting pressure in ways that create their own seismic signatures. As the magma chamber expands, it pushes upward against the overlying crust, causing the ground surface to rise by inches or sometimes feet. This process, called inflation, happens so slowly that you would never notice it during your lifetime. But sensitive GPS instruments can track these movements with precision measured in millimeters. Different types of volcanic tremors tell different stories about what is happening in the hidden depths. Some earthquakes occur directly beneath the magma chamber as the rock fractures under pressure. Others occur along the pathways where magma is forcing its way upward through the crust, each fracture releasing a pulse of seismic energy. Still others happen as older rock formations adjust to the changing stresses, like a house settling as its foundation shifts. The most mysterious tremors of all are the harmonic tremors, continuous rhythmic vibrations that can last for hours or days. These are not the sharp, sudden jolts of typical earthquakes, but sustained oscillations that suggest magma is moving continuously through underground channels. Scientists think these tremors are created by the flow of gas-rich magma through narrow conduits, like the sound of wind blowing across the mouth of a bottle, but amplified through miles of solid rock. As you rest in the comfort of your bed, consider how these seismic signals travel outward from their volcanic sources, carrying information about deep earth processes to instruments scattered across the globe. The waves that begin as tiny fractures in rock beneath the volcano might be detected by seismometers in neighboring countries, their patterns analyzed by computers that can distinguish volcanic earthquakes from the tremors caused by ocean waves, wind, or human activity. Each volcanic system speaks with its own unique seismic voice.
The broad, gentle shield volcanoes of Hawaii create different earthquake patterns than the steep-sided stratovolcanoes of the Andes. Volcanoes that tend toward explosive eruptions generate different types of pre-eruption tremors than those that typically produce flowing lava. Over decades of careful listening, seismologists have learned to recognize these individual voices, to distinguish between the seismic signatures of different types of volcanic behavior. But perhaps the most remarkable aspect of Earth's seismic language is how it reveals the interconnectedness of our planet's geological systems. When a large earthquake occurs on one side of the Pacific Ocean, the seismic waves it generates travel completely through Earth's interior, emerging on the opposite side of the planet where they can be detected by sensitive instruments. These global seismic signals carry information about the deep structure of our planet, the boundaries between different layers, the temperature and density variations in the mantle, the hidden architecture of the world beneath our feet. The study of volcanic earthquakes has revealed that magma chambers are far more complex than simple underground balloons filled with molten rock. Instead, they exist as intricate networks of interconnected pockets, dikes, and sills, each with its own seismic personality. As magma moves through this underground plumbing system, it creates a cascade of tiny earthquakes that map out the pathways in three-dimensional detail, like a medical scan revealing the circulatory system of the deep Earth. Temperature changes in the magma system also create their own seismic effects. As hot magma intrudes into cooler rock, the thermal expansion and contraction create stresses that generate earthquake swarms, clusters of small tremors that occur over periods of days or weeks. These thermal earthquakes often precede volcanic eruptions by months or years, providing early warning of changes occurring deep beneath the surface. The most subtle seismic signals come from the gases dissolved in the magma itself. As rising magma moves into regions of lower pressure, dissolved water vapor and carbon dioxide begin to form bubbles, like champagne when the cork is popped. This degassing process creates its own unique pattern of micro-earthquakes, each bubble formation and collapse generating tiny seismic pulses that sensitive instruments can detect and analyze. Modern volcano monitoring has become an art of listening to these multiple seismic voices simultaneously, using networks of instruments that can pinpoint the location of earthquakes to within a few hundred yards and depths to within a mile or less. Computer algorithms analyze thousands of tiny tremors every day, looking for the subtle patterns that indicate when a volcanic system might be moving toward eruption. The patience required for this kind of scientific listening mirrors the patience of the volcanic systems themselves. Some volcanic earthquake swarms continue for months or years without leading to eruptions. Others build rapidly over days or weeks before culminating in dramatic surface activity. The seismic language of volcanoes operates on timescales that span human lifetimes, requiring generations of scientists to build the knowledge needed to interpret Earth's whispered warnings. As these tremors travel through the bedrock beneath your sleeping place, they carry with them not just information about volcanic processes, but evidence of the dynamic, living nature of our planet. Every seismic wave is proof that Earth is not a static, unchanging sphere, but a world in constant motion, constantly reshaping itself through forces that operate on scales of time and pressure that dwarf human experience. And as the frequency and intensity of these underground tremors gradually increase, as the seismic whispers grow stronger and more insistent, they herald the approach of something magnificent and terrible. The moment when all the mounting pressure, all the accumulated heat, all the patient accumulation of molten rock finally reaches the threshold where Earth can no longer contain its inner fire, and the mountain itself begins to breathe with flame. There comes a moment in the deep conversation between earth and sky, when all the patient accumulation of heat and pressure, all the slow gathering of molten rock in hidden chambers, all the whispered warnings carried by trembling stone, finally converge into something magnificent and transformative. This is the moment when mountains learn to breathe fire, when solid rock becomes liquid light, when the boundary between the hidden world below and the familiar world above dissolves in fountains of glowing stone that reach toward the stars. Picture yourself in the moments before this awakening, when the seismic whispers we followed through darkness have grown into more insistent voices, when the magma chamber beneath the mountain has swollen beyond the capacity of its rocky walls to contain it. The pressure has been building for decades, perhaps centuries, like air slowly pumped into a balloon until the rubber stretches to its absolute limit. But unlike a balloon, the rock above a magma chamber doesn't simply pop. It yields gradually, magnificently, in ways that create some of the most spectacular displays of natural power on Earth. The first sign that the mountain is preparing to breathe often comes not as fire, but as changes in the landscape itself. The ground begins to bulge upward as the magma chamber expands, creating subtle domes that grow by inches each day. Springs that have flowed cold for generations suddenly warm, carrying the taste of deep minerals to the surface. Fumaroles, vents where volcanic gases escape, begin to appear like small holes punched in the skin of the mountain, releasing wisps of steam that carry the sulfurous breath of the deep earth. As the magma rises through the final miles of its journey, it encounters rock that has never felt such heat, never experienced such pressure. The temperature difference between the rising magma and the cool surface rock creates thermal stresses that crack the stone like pottery cooling too quickly from a kiln. Each crack releases a pulse of seismic energy, creating earthquake swarms that build in intensity like the crescendo of a symphony approaching its climactic movement. But the most dramatic changes occur within the magma itself as it approaches the surface. Deep in the chamber, under enormous pressure, gases like water vapor and carbon dioxide remain dissolved in the molten rock like champagne under pressure in an unopened bottle. As the magma rises and pressure decreases, these gases begin to come out of solution, forming bubbles that make the magma foam like boiling milk. The process accelerates rapidly. The more bubbles form, the lighter the magma becomes. The faster it rises, the more rapidly additional gases escape from solution. When the rising magma finally reaches the surface, the character of the eruption depends entirely on the delicate balance between the magma's composition, its gas content, and the pathway it has carved through the overlying rock.
If the magma is relatively fluid and the gases can escape easily, the mountain breathes gently, producing the serene lava fountains and flowing rivers of molten rock that build shield volcanoes like those in Hawaii. These eruptions unfold like slow-motion fireworks, with curtains of liquid stone arcing gracefully through the air before settling into streams that glow like terrestrial rivers of starlight. Watch in your imagination as a gentle eruption begins. The first sign might be a small crack appearing in the mountainside, glowing cherry red as superheated gases escape. Within hours or days, this crack widens into a fissure from which molten lava begins to emerge like thick honey poured from a cosmic spoon. The lava doesn't explode violently into the air. Instead, it wells up and overflows, following the topography of the landscape as it seeks the lowest pathways down the mountainside. The temperature of this flowing lava exceeds 2,000 degrees Fahrenheit, hot enough to melt copper, hot enough to ignite trees from hundreds of feet away simply through radiant heat. Yet it moves with surprising gentleness, flowing at speeds you could easily outrun, giving forests and communities time to evacuate while the molten rock slowly claims the landscape. As the lava flows, it cools and develops a skin of solid rock while remaining molten within, creating tunnels through which the liquid stone continues to travel for miles from its source. But when the magma contains high levels of silica and trapped gases, the mountain's breath becomes far more dramatic. This thick, gas-rich magma cannot flow peacefully to the surface. Instead, it plugs the volcanic vent like a cork in a bottle, allowing pressure to build until the mountain finally explodes with the force of thousands of atomic bombs. The eruption column that results can tower 20, 30, even 50 miles into the sky, punching through the troposphere and stratosphere to deposit volcanic ash in the realm where satellites orbit. Imagine witnessing such an explosive eruption from a safe distance. The mountain seems to split open along its flanks, releasing a mixture of gas, ash, and molten rock fragments that roars skyward at velocities approaching the speed of sound. The eruption column glows with its own internal lightning as electrically charged particles of volcanic glass collide within the rising plume. The sound of the eruption travels for hundreds of miles, a deep rumbling that you feel in your chest as much as you hear with your ears. Within this towering column, fragments of molten rock cool rapidly in the thin air, forming volcanic glass that shatters into countless tiny shards. These particles of ash, each one a miniature work of art, with complex crystalline structures, rise on the power of superheated gases before beginning their slow descent back to Earth. The finest particles might circle the globe for months, creating spectacular sunsets and temporarily cooling Earth's climate by reflecting sunlight back to space. As the eruption continues, the dynamics within the volcanic system create an intricate dance between destruction and creation. Pyroclastic flows, avalanches of superheated gas and volcanic debris race down the mountainsides at speeds exceeding 100 miles per hour, their temperatures hot enough to incinerate everything in their path. Yet these same flows, when they finally come to rest and cool, create some of the most fertile soils on Earth, setting the stage for lush forests and productive agriculture in future decades.
The volcanic gases released during eruptions tell their own story of deep Earth chemistry. Water vapor, the most abundant volcanic gas, represents moisture that has been locked in rock formations for millions of years, now returned to the atmosphere to eventually fall again as rain. Carbon dioxide released from volcanic eruptions adds to the atmospheric inventory of greenhouse gases, while sulfur compounds create aerosols that can influence global weather patterns for years after major eruptions. Even the most violent eruptions follow patterns that reveal the underlying physics of how gas and liquid behave under extreme conditions. The height of an eruption column depends on the balance between the upward momentum of the escaping gases and the downward pull of gravity on the ash particles. The shape of the eruption cloud, whether it forms a narrow column or spreads into a broad umbrella, depends on wind patterns in the upper atmosphere and the rate at which volcanic material is being ejected from the vent. As you observe these magnificent displays of volcanic power in your imagination, notice how each eruption is simultaneously an ending and a beginning. The explosive release of pressure marks the end of a cycle that may have been building for decades or centuries. The magma chamber partially empties, the mountain deflates slightly. The seismic activity gradually diminishes as the system returns toward equilibrium. Yet, at the same time, the eruption creates new land, new minerals, new possibilities for life to establish itself in landscapes transformed by fire. The volcanic debris spread across the countryside begins immediately to weather and break down, releasing nutrients that will nourish plants for generations to come. The fresh lava flows, once they cool and solidify, become the foundation stones for future ecosystems. The ash deposited in distant lands enriches soils and preserves a record of the eruption that scientists will be able to read thousands of years in the future. But perhaps the most remarkable aspect of volcanic eruptions is how they connect the most local and the most global scales of Earth's behavior. A mountain breathing fire in one location affects atmospheric chemistry worldwide. Volcanic ash travels across oceans and continents. The heat released during major eruptions can be detected by satellites orbiting hundreds of miles above the Earth's surface. The sulfur compounds ejected into the stratosphere can create spectacular sunsets visible from thousands of miles away. As the immediate drama of the eruption begins to subside and the mountain settles back into a period of rest, the real work of volcanic creation is just beginning. The hot ash and lava that seemed so destructive in the moment of their release are now raw materials for transformation, the ingredients from which new landscapes, new ecosystems, new possibilities for life will emerge. The mountain's fiery breath, so dramatic in its release, becomes the foundation for gardens of stone and steam, where life will find ways to flourish in conditions that stretch the very definition of what it means to be alive. In the quiet aftermath of the mountain's fiery breath, when the ash has settled and the lava has cooled to black stone, something miraculous begins to unfold. What seemed like complete destruction reveals itself as the foundation for an extraordinary renaissance of life. The volcanic landscapes that appeared so barren and hostile in the immediate wake of eruption slowly transform into gardens of stone and steam, where life discovers ways to flourish in conditions that stretch the very definition of what it means to be alive. Picture yourself walking through a volcanic landscape several years after an eruption, when the initial drama has faded, but the creative work of geological rebirth is just beginning. The ground beneath your feet crunches with volcanic glass, and the air carries the faint mineral tang of sulfur compounds still escaping from cooling lava flows. Yet already, in cracks between the black rocks, you might notice the first brave pioneers of the plant kingdom, tiny ferns unfurling from spores that survived the heat, mosses beginning to paint the dark stone with patches of brilliant green. These volcanic soils, born from the breakdown of fresh lava and ash, possess a richness that seems almost magical. The molten rock that once destroyed everything in its path carried with it a treasure trove of mineral nutrients from deep within the earth: potassium, phosphorus, magnesium, iron, and dozens of trace elements that plants need to thrive. As the volcanic glass weathers under the patient influence of rain and wind, these nutrients are slowly released, creating soils of extraordinary fertility. The process of soil formation on volcanic landscapes follows a rhythm that spans decades and centuries. Rainwater, slightly acidic from dissolved carbon dioxide, begins to chemically attack the fresh volcanic glass, breaking down its crystal structure and releasing the minerals locked within. Pioneer bacteria and lichens establish themselves on the rock's surfaces, their biological processes accelerating the weathering and beginning to build the thin films of organic matter that will eventually become rich soil. But perhaps the most enchanting aspects of volcanic landscapes are the hot springs and geysers that bubble up where underground heat sources meet groundwater. These natural fountains of warm, mineral-rich water create oases of life in otherwise stark volcanic terrain. The water that emerges from these springs has traveled deep underground, sometimes for decades or centuries, slowly warming as it circulates through fractured rock near cooling magma chambers. Imagine dipping your hand into one of these volcanic hot springs. The water feels silky against your skin, warmed to temperatures that range from merely comfortable to almost scalding. This silky texture comes from dissolved minerals, silica, calcium, magnesium, and exotic trace elements like lithium and boron that give the water properties unlike anything that flows from ordinary surface sources. As this mineral-rich water flows away from its source, it deposits its dissolved cargo in intricate terraces and formations that grow like underwater coral reefs exposed to air. The terraced pools of places like Yellowstone's Mammoth Hot Springs or Turkey's Pamukkale represent thousands of years of mineral deposition, each thin layer recording slight changes in water chemistry, flow rates, and temperature. The calcium carbonate terraces build up grain by grain, creating stepped landscapes that look like frozen waterfalls or giant staircases carved from living stone. These formations grow so slowly that you could watch them for a lifetime without noticing any change. Yet they represent some of the most active geological processes on Earth's surface. Within these hot springs, life takes forms that challenge everything we thought we knew about the limits of biological existence. Thermophilic bacteria, literally heat-loving microorganisms, thrive in water temperatures that would cook most other forms of life. These remarkable organisms not only survive in boiling water, but actually require such extreme conditions to carry out their biological processes. They represent some of the most ancient forms of life on Earth, descendants of the microorganisms that first evolved when our planet was much hotter and more volcanic than it is today. The colors that paint volcanic hot springs come from these extremophile communities. Brilliant orange mats of bacteria thrive in water approaching the boiling point. Bright yellow colonies prefer slightly cooler temperatures. Green algae establish themselves where the water has cooled to merely warm. As you move away from the hottest source of a hot spring, you can literally see the temperature gradient painted in living color. Each band representing a different community of organisms adapted to specific thermal conditions. These bacterial communities don't just survive in volcanic environments, they actively transform them. Some bacteria precipitate minerals from the hot spring water, helping to build the terrasque formations. Others metabolize sulfur compounds, creating the distinctive rotten egg smell of many volcanic areas, while converting toxic chemicals into harmless compounds. Still others fix nitrogen from the atmosphere, making this essential nutrient available to the plants that will eventually colonize the cooling volcanic soils. The chemistry of volcanic hot springs reads like a catalog of Earth's mineral wealth. Waters that have circulated through volcanic rocks emerge enriched with elements that are rare in surface environments. Gold, silver, mercury, and other precious metals concentrate in hot spring deposits. Rare earth elements essential for modern technology accumulate in the mineral crusts. These springs represent natural laboratories where we can study the processes that concentrate valuable minerals in the Earth's crust. As volcanic landscapes age and cool, they become increasingly hospitable to more familiar forms of life. The first plants to colonize fresh lava flows are often specialists in survival. Species that can tolerate extreme conditions, fix their own nitrogen from the atmosphere, and establish themselves with minimal soil. Ohia trees in Hawaii, birch trees in Iceland, and hardy grasses on volcanic slopes worldwide represent nature's advanced scouts, the pioneers that prepare the way for the diverse ecosystems that will follow. The succession of plant communities on aging volcanic landscapes follows predictable patterns that play out over decades and centuries. Fast-growing, short-lived species establish themselves first, creating shade and organic matter that moderate the harsh conditions for the species that follow. Nitrogen-fixing plants establish symbiotic relationships with bacteria that can extract this essential nutrient from the atmosphere, gradually enriching the developing soil. Each generation of plants makes the environment slightly more hospitable for the next wave of colonizers. Wildlife follows the plants in waves of increasing diversity and complexity.
Insects arrive first, often carried by wind from distant areas. Spiders follow the insects. Birds discover the new habitat and bring seeds from other ecosystems in their digestive systems and on their feathers. Small mammals find shelter among the growing vegetation. Gradually, what began as a sterile landscape of fresh volcanic rock develops into a complex ecosystem with its own unique character shaped by its volcanic origins. The fertility of mature volcanic soils has supported some of Earth's most productive agricultural regions. The slopes of Vesuvius, despite their obvious risks, have been continuously cultivated for thousands of years because the volcanic soil produces exceptional crops. Coffee grown on volcanic soils develops distinctive flavors prized by connoisseurs. Wine grapes cultivated in volcanic regions produce vintages with unique mineral characteristics that reflect the geological foundations of their vineyards. But perhaps the most remarkable aspect of these gardens of stone and steam is how they demonstrate life's extraordinary adaptability and resilience. Every volcanic landscape tells a story of destruction followed by renewal, of apparent endings that become new beginnings. The same forces that can obliterate existing ecosystems in moments also create the raw materials for new forms of life to explore and exploit. Modern research in volcanic environments has revealed that these landscapes serve as natural laboratories for understanding some of the most fundamental processes in biology and geology. Scientists study volcanic hot springs to understand how life might survive in extreme environments on other planets. The rapid evolution of organisms in isolated volcanic environments provides insights into how species adapt to new conditions. The mineral deposits forming in real time around hot springs help us understand how valuable ore deposits formed in Earth's ancient past. As you rest in the comfort of imagining these gardens of stone and steam, consider how they represent hope made manifest in the natural world. They remind us that destruction is often followed by creation, that the most severe disruptions can become opportunities for new forms of beauty and abundance to emerge. The volcanic landscapes that seem so hostile and barren in their youth mature into some of Earth's most fertile and biologically diverse regions. These volcanic gardens also connect us to the deep rhythms of geological time, where human lifespans represent brief moments in cycles of destruction and renewal that have been operating for billions of years. Each hot spring bubbling with mineral-rich water, each fern unfurling from a crack in fresh lava, each new soil grain weathering from volcanic glass represents a chapter in the ongoing story of how Earth continuously reinvents itself. And as these individual gardens of stone and steam scattered across the globe accumulate and mature over geological time, they become part of something even grander, a planetary network of volcanic activity that forms a ring of fire around the largest ocean, connecting distant continents through the ancient songs of tectonic plates in motion. If you could rise high above Earth and look down upon the Pacific Ocean from space, you would see something extraordinary. A horseshoe-shaped necklace of volcanic light that encircles the world's largest body of water like a crown of fire worn by the planet itself. This is the Ring of Fire, a 25,000-mile arc of volcanic activity that connects the snow-capped peaks of Alaska to the tropical islands of Indonesia.
linking the cherry blossoms of Japan to the wine valleys of Chile in a single, continuous song of geological activity that has been playing for hundreds of millions of years. The Ring of Fire is not just a collection of individual volcanoes scattered randomly around the Pacific's edge. It is a single, integrated system that tells the story of how Earth's surface moves and changes over deep time. Each volcano along this ring is like a single note in a vast symphony, connected to all the others through the slow dance of tectonic plates that carry entire continents across the surface of our planet like passengers on geological rafts that move at the speed fingernails grow. Picture yourself beginning a journey around this ring of fire, starting in the cold volcanic islands of Alaska's Aleutian chain. Here, where the Pacific plate slides beneath the North American plate in a process called subduction, the ocean floor itself is being recycled back into Earth's interior. As the oceanic plate descends into the hot mantle, it carries with it millions of years of accumulated sediments, the shells of ancient sea creatures, the remains of prehistoric forests, the chemical signatures of long-vanished climates. The descending oceanic plate doesn't simply melt as it sinks into the mantle. Instead, it releases water and other volatile compounds that have been locked in its crystal structure since it first formed on the ocean floor. This water, superheated under enormous pressure, rises into the overlying mantle rock and lowers its melting point, creating the magma that feeds the volcanic chain. Each Aleutian volcano is thus fed by materials that once lay on the bottom of the Pacific Ocean, transformed by heat and pressure into molten rock that erupts in landscapes thousands of miles from where its constituent atoms last saw sunlight. As you continue your imaginary journey southward along the Ring of Fire, you encounter the volcanic peaks of the Cascade Range, where Mount Rainier, Mount Shasta, and their siblings stand as monuments to millions of years of subduction. These towering stratovolcanoes, built layer by layer from countless eruptions, represent some of the most explosive volcanic systems on Earth. Their steep-sided profiles and snow-covered peaks belie the tremendous forces that created them, the collision between oceanic and continental plates that continues to this day. The journey eastward across the Pacific brings you to Japan, where the Ring of Fire reveals another aspect of its complex personality. Here, not one, but multiple tectonic plates converge in a geological knot of extraordinary complexity. The Pacific Plate, the Philippine Sea Plate, the Eurasian Plate, and the North American Plate all meet in the vicinity of Japan, creating a landscape where volcanic activity, earthquake activity, and mountain building occur with an intensity found nowhere else on Earth. Mount Fuji, Japan's most iconic volcano, rises from this tectonic complexity like a perfect geometric cone painted against the sky. But Fuji is far from alone. The Japanese archipelago hosts more than 100 active volcanoes, each one a window into the deep processes occurring where oceanic plates slide beneath the Asian continent. The volcanic hot springs that are so central to Japanese culture, the fertile soils that support intensive agriculture, even the distinctive mineral content of Japanese sake, all reflect the volcanic foundations of these islands. Continuing southward through the western Pacific, the Ring of Fire leads through the Philippines, where more than 300 volcanoes dot the landscape of over 7,000 islands. This region represents one of the most volcanically active areas on Earth, where the complex interactions between the Pacific, Philippine Sea, and Indo-Australian plates create a three-dimensional puzzle of subduction zones, volcanic arcs, and active fault systems. The 1991 eruption of Mount Pinatubo here injected so much sulfur dioxide into the stratosphere that it temporarily cooled global temperatures by half a degree Celsius, demonstrating how local volcanic activity can have planetary consequences. The Ring of Fire reaches its most complex expression in Indonesia, where the collision between the Indo-Australian and Eurasian plates has created the most volcanically active region on Earth. With more than 130 active volcanoes, Indonesia hosts about 13% of all the world's active volcanoes in less than 2% of the world's land area. This is where Krakatoa exploded in 1883 with such violence that the sound was heard 3,000 miles away, where Tambora's 1815 eruption caused global climate change and crop failures, where the ongoing creation of new volcanic islands demonstrates the Ring of Fire's power to literally create new land from the ocean floor. As your imaginary journey continues eastward across the Pacific, you encounter a different expression of the Ring of Fire's activity: the volcanic islands and seamounts that rise from the deep ocean basin itself. These are not formed by subduction, but by hotspots in the Earth's mantle that remain stationary while the Pacific plate moves overhead, creating chains of volcanic islands like the Hawaiian archipelago and the Emperor Seamount chain that extends northward toward Alaska. The eastern rim of the Ring of Fire presents yet another geological personality as you travel along the volcanic peaks of the Andes Mountains. Here, the Nazca Plate slides beneath the South American Plate, creating the longest continuous mountain chain on Earth and hosting some of the world's highest active volcanoes. The thin air at these altitudes means that volcanic eruptions can send ash columns higher into the atmosphere than at any other location on Earth, sometimes reaching altitudes where commercial aircraft cruise. The Ring of Fire completes its circuit in Central America and Mexico, where the small oceanic plates of the Eastern Pacific, the Cocos Plate and the Rivera Plate, slide beneath the North American Plate, creating the volcanic peaks that rise above the tropical landscapes of Guatemala, Costa Rica, and western Mexico. These volcanoes often rise directly from the ocean or from coastal plains, creating dramatic landscapes where snow-capped volcanic peaks tower over tropical beaches and coral reefs. But perhaps the most remarkable aspect of the Ring of Fire is not its individual components, but how they all work together as a single, integrated system. The movement of tectonic plates around the Pacific Basin is not random. It follows patterns that have persisted for hundreds of millions of years, driven by convection currents in Earth's mantle that operate like a planetary-scale heat engine. The Pacific Plate, the largest tectonic plate on Earth, acts like a giant conveyor belt, carrying volcanic islands and seamounts from their birthplaces at mid-ocean ridges toward their eventual destruction in subduction zones. This grand circulation system means that rocks now being subducted along the western edge of the Ring of Fire may have formed at mid-ocean ridges along the eastern Pacific centuries of millions of years ago. The atoms in a volcanic eruption in Japan may have last seen the surface of the Earth when they were part of coral reefs in the ancient Pacific. The Ring of Fire thus represents not just current volcanic activity, but a continuous recycling system that has been mixing and remixing Earth's surface materials for geological eons. The timing of volcanic activity around the Ring of Fire also shows subtle connections that suggest the system operates as an integrated whole. Large earthquakes in one part of the ring sometimes trigger increased volcanic activity in distant regions, as seismic waves travel through Earth's interior and disturb magma chambers thousands of miles away. Statistical studies have revealed patterns in the timing of major eruptions around the Pacific Rim that suggest the various volcanic systems communicate with each other through mechanisms we are only beginning to understand. Modern satellite monitoring has revealed that the Ring of Fire is even more active than we previously realized. Infrared sensors can detect the heat signatures of volcanic activity day and night, while radar instruments can measure ground deformation associated with magma movement. These technological eyes in the sky have shown us that volcanic systems around the Pacific Rim are constantly changing, growing, shrinking, heating, cooling, inflating, deflating, in a complex dance of geological activity that never truly stops. The Ring of Fire also serves as Earth's primary mechanism for transferring heat from the interior to the surface. The volcanic activity around the Pacific Rim represents one of the main pathways by which heat generated by radioactive decay in Earth's core and mantle escapes to space. Without this release valve, Earth's interior would be even hotter, and the dynamics of plate tectonics that drive the ring's activity might operate very differently. As you complete your imaginary journey around the Ring of Fire and return to your starting point, you carry with you an appreciation for one of Earth's grandest geological features, a planetary-scale system that connects distant continents through deep time processes, that creates new land while destroying old, that brings deep Earth materials to the surface while recycling surface materials back to the depths. The Ring of Fire represents Earth as a living, breathing, dynamic planet where nothing remains static for long, where today's ocean floor becomes tomorrow's mountain range, where volcanic islands rise from the depths and eventually return to them.
This ancient song of the Ring of Fire played out over millions of years in the language of earthquakes and eruptions, mountain building and ocean floor spreading, connects all of us who live around the Pacific Rim in a shared geological destiny. And as this grand tectonic symphony continues to play, it writes new chapters in Earth's history, while preparing the stage for one of the most remarkable aspects of volcanic creation, the birth of entirely new islands from the ocean's depths. Imagine the deepest part of the ocean, where no sunlight has ever penetrated, where the pressure would crush any surface-dwelling creature instantly, where the water temperature hovers just above freezing in eternal darkness. Here, more than 3 miles beneath the rolling waves of the Pacific, on a seafloor carpeted with the finest sediments that have been settling for millions of years, something miraculous is beginning to happen.
A crack appears in the basaltic crust of the ocean floor, glowing cherry red in the absolute darkness. And from this crack begins to emerge one of Earth's most remarkable creations, a volcanic island being born from the deepest dreams of the sea. This is not the explosive, dramatic volcanism of the Ring of Fire we journeyed around in darkness. This is something gentler, more patient, more persistent. The birth of land from the ocean's depths through a process that unfolds over millions of years, building paradise grain by grain from molten rock that rises from sources so deep in the earth that they remain stationary, while entire continents drift overhead like clouds across the sky. The Hawaiian island chain, stretching like a string of emeralds across the blue immensity of the Pacific, tells the story of this deep ocean volcanism more clearly than any other place on Earth. Each island in the chain represents a moment when the Pacific plate, moving steadily northwestward at about the same rate your fingernails grow, passed over a mantle hotspot, a column of superheated rock rising from depths approaching the boundary between Earth's core and mantle, nearly 1,800 miles below the surface. Picture yourself descending through the ocean above an active underwater volcano, following the column of rising magma from its source in the deep mantle to its emergence on the sea floor. The journey begins in regions of Earth's interior where temperatures exceed 3,000 degrees Fahrenheit, where rock exists in a state between solid and liquid, where convection currents as large as continents slowly rise and fall in cycles measured in hundreds of millions of years. The mantle plume that feeds Hawaiian volcanism is like a blowtorch pointed upward from the deepest parts of Earth's interior, maintaining its position relative to Earth's core, while the Pacific plate slides overhead like a piece of paper moving across a candle flame. As this column of superheated mantle rock rises toward the surface, it begins to melt, not because it's getting hotter, but because the pressure decreasing as it rises allows the solid rock to transform into liquid magma. By the time this rising column of molten rock reaches the base of the oceanic crust, it has traveled 1,800 miles of solid earth, carrying with it chemical signatures of the deepest parts of our planet. This deep mantle magma is different from the recycled oceanic crust that feeds Ring of Fire volcanism. It's more primitive, closer in composition to the original materials from which Earth formed 4.6 billion years ago, enriched with rare isotopes and trace elements that provide scientists with clues about conditions in Earth's unreachable interior. When this deep-sourced magma finally breaches the seafloor and begins to build a volcano, the process unfolds with a patience that dwarfs human timescales. The first eruptions occur in water so deep that the enormous pressure prevents the formation of gas bubbles, creating distinctive pillow-shaped masses of basaltic lava that stack upon each other like geological cushions. These pillow lavas cool rapidly in the frigid seawater, forming glassy rinds around molten cores, creating textures and structures that can only form in the deep ocean environment. For hundreds of thousands of years, the growing volcano remains completely submerged, building its foundation in absolute darkness. Layers of pillow lava accumulate with volcanic sediments, creating a broad, gently sloped shield that may eventually cover thousands of square miles of seafloor, while remaining invisible to any surface observer. The volcano is already enormous, larger than any mountain on any continent. Yet it exists in a realm that humans can visit only in the most sophisticated deep-sea vehicles. As the volcano continues to grow, layer by patient layer, its summit slowly approaches the depth where seawater begins to interact differently with the emerging lava. At depths of a few thousand feet, the reduced pressure allows volcanic gases to begin forming bubbles, changing the character of the eruptions from the gentle effusion of pillow lavas to more vigorous fountaining that builds the volcanic edifice more rapidly. The transition from submarine to subaerial volcanism, the moment when the growing volcano finally breaks the surface of the ocean, represents one of the most dramatic transformations in geology. Suddenly, lava that has been cooling rapidly in seawater encounters air, allowing it to form the flowing rivers of molten rock that build the classic shield volcano profile we associate with Hawaiian volcanoes. The summit of the volcano, which may have been growing in darkness for 1,000,000 years, suddenly emerges into sunlight for the first time. But even this emergence is rarely a single dramatic event. More often, the growing volcano creates a series of temporary islands that appear and disappear as eruptions wax and wane, as wave action erodes fresh lava, as the delicate balance between volcanic construction and oceanic destruction plays out over decades or centuries. The newborn island fights for its existence against the relentless power of ocean waves, which can destroy in days what took decades of volcanic activity to create. Once established above sea level, the volcanic island begins a new phase of its existence. No longer cooled by the infinite heat sink of the ocean, the lava flows can travel much farther from their source, creating the broad, gentle slopes that characterize shield volcanoes. These flows often reach the sea, where they create spectacular displays as 2,000-degree lava meets seawater, generating enormous clouds of steam and building new coastline grain by grain as the molten rock cools and solidifies. The island continues to grow not just upward but outward as countless lava flows build new land along its shores. Each flow adds to the island's area, creating distinctive geological formations like black sand beaches where volcanic glass has been ground fine by wave action. Sea cliffs carved from layered lava flows that reveal the island's growth history like rings in a tree, and tide pools formed in the irregular surfaces of cooled lava flows. As the Pacific Plate continues its northwestward motion, carrying the newly formed island away from its hotspot source, the character of the volcanism begins to change. The steady supply of deep mantle magma starts to diminish as the distance between the island and the stationary hotspot increases. Eruptions become less frequent, less voluminous, and eventually cease altogether as the island is carried beyond the reach of the deep mantle plume that gave it birth. But the hotspot doesn't disappear. It continues to melt through the overlying Pacific Plate, beginning the birth of a new island to the southeast of the aging one.
This process has been repeating for at least 70 million years, creating the Hawaiian Emperor Island chain that stretches from the currently active Big Island of Hawaii all the way to the Aleutian Trench near Alaska, where the oldest volcanic islands in the chain are finally being subducted back into Earth's interior. Each island in the chain thus represents a snapshot of hotspot volcanism at a different stage of development. The Big Island of Hawaii, currently positioned over the hotspot, hosts active volcanoes like Kilauea and Mauna Loa that continue to add new land to the island's surface. Moving northwest along the chain, each successive island is older, more eroded, and more distant from its volcanic source. Maui, Oahu, and Kauai show progressively more advanced stages of volcanic evolution and erosion. The youngest member of the Hawaiian chain hasn't even broken the surface yet. Loihi Seamount, located about 22 miles southeast of the Big Island's current shoreline, represents the next Hawaiian island in the making. Rising more than 10,000 feet from the seafloor, Loihi still has about 3,000 feet to grow before it breaks the surface and begins its existence as a true island. Current estimates suggest this emergence might occur within the next 10,000 to 100,000 years, tomorrow in geological terms. The birth of volcanic islands from ocean depths represents more than just geological processes. It demonstrates how isolated ecosystems develop and evolve. When a new island first emerges from the sea, it is essentially sterile, lacking any form of life except perhaps some hardy bacteria. Over time, plants and animals arrive by wind, by ocean currents, and eventually by their own flying or swimming abilities, establishing ecosystems that are both related to and distinct from those on other landmasses.
These island ecosystems become natural laboratories for understanding evolution and adaptation. Species that arrive on newly formed islands often evolve rapidly to fill ecological niches that don't exist elsewhere, developing unique characteristics found nowhere else on Earth. The endemic species of oceanic islands, from Darwin's finches in the Galapagos to the Hawaiian honeycreepers, provide some of the clearest examples of evolution in action. The formation of volcanic islands also influences global ocean circulation and climate patterns. Large volcanic islands can redirect ocean currents, create their own weather patterns through orographic effects, and even influence the formation of clouds and precipitation thousands of miles away. The Hawaiian Islands, for example, create a wake in the trade wind patterns that can be detected far downstream in satellite images. Modern technology has allowed us to witness island birth in real time. Underwater cameras have recorded the moment when pillow lavas first emerge from seafloor fissures. Satellite imagery has captured the growth of new islands like Surtsey near Iceland, which emerged from the ocean in 1963 and continues to evolve today. These observations have revolutionized our understanding of how quickly geological processes can operate when viewed on human timescales rather than geological ones. The volcanic islands born from the ocean depths also serve as bridges between the deep earth and the surface environment.
The basaltic lavas that form these islands carry information about conditions in the deep mantle, preserving chemical signatures that allow scientists to study parts of Earth that will never be directly accessible. Isotope ratios in Hawaiian lavas provide clues about the composition of the deep mantle, the age of recycled materials, and the dynamics of convection in Earth's interior. As you rest in the comfort of imagining these islands rising from the deepest parts of the ocean, consider how they represent hope and persistence made manifest in stone. Each island is a testament to the power of gradual processes, to the way small, consistent actions can accumulate over time to create something magnificent and permanent. From the darkness of the deep sea floor, through patience measured in millennia, paradise literally rises to meet the light. These oceanic islands also remind us that Earth is constantly creating new land, new opportunities for life, new landscapes for future generations to explore and cherish. The island that breaks the surface today may become the site of tropical forests, coral reefs, and communities of endemic species found nowhere else in the universe. In the birth of islands from ocean depths, we see Earth not as a finished creation, but as a world still in the process of becoming, still writing new chapters in the eternal story of stone and sea, fire and water, destruction and creation. As our journey through the fiery heart of Earth draws to its gentle close, settle deeper into the comfort of your bed and let your mind expand to embrace the grandest truth that volcanoes teach us, that our planet exists in a state of eternal becoming, where nothing remains fixed forever, where the solid ground beneath your feet participates in cycles of transformation so vast and patient that they dwarf human comprehension, yet connect intimately to every breath you take, every atom in your body, every grain of soil in your garden. The volcanic processes we have followed together, from the sleeping giants in deep chambers to the islands rising from the ocean depths, are not separate phenomena, but movements in a single magnificent symphony that has been playing since Earth first formed from cosmic dust 4.6 billion years ago. This is the rock cycle, the slow circulation of materials between Earth's interior and surface that ensures our planet remains geologically alive, constantly renewing itself through processes that operate on timescales measured in millions and hundreds of millions of years. Picture in your drowsy imagination the complete journey of a single grain of quartz sand lying on a beach somewhere along the Pacific coast. This tiny crystal, smaller than the period at the end of this sentence, carries within its atomic structure a history that spans geological eons. Perhaps it began its existence billions of years ago as part of a granite intrusion that cooled slowly in a deep magma chamber, its silicon and oxygen atoms arranging themselves into the perfect hexagonal symmetry that defines quartz crystal structure. For millions of years, this grain might have rested in darkness, part of a vast underground body of crystalline rock, while continents drifted overhead, and mountain ranges rose and fell in the world above.
Eventually, the slow work of erosion, the patient action of groundwater, the gradual expansion and contraction caused by temperature changes, the inexorable forces of weathering, freed the grain from its granitic host and began its journey toward the surface. Released into sunlight for the first time in its existence, the grain joined countless others in streams and rivers that carried it toward the sea, tumbling and rolling, gradually becoming rounded and polished by its collision with other rock fragments. Along the way, it might have been deposited temporarily in river deltas, buried under layers of sediment, compressed into sandstone, then lifted up again as part of mountain-building processes, and weathered out once more to continue its journey. Finally reaching the ocean, the grain settled into marine sediments, where it might have rested for millions more years, slowly being buried under younger layers of sand and mud, compressed and cemented into solid rock once again. But the story doesn't end there, because the seafloor itself is not permanent. It too participates in the grand cycles of planetary renewal. As oceanic plates move toward subduction zones, carrying their cargo of sedimentary rocks toward trenches where they will be consumed by Earth's interior, our grain of quartz faces a choice of fates determined by the precise conditions it encounters. If the temperature and pressure of subduction are just right, the grain might be heated enough to become part of a new magma that will eventually feed volcanic eruptions, its atoms dispersed into volcanic ash that will settle on distant landscapes to begin new cycles of rock formation. Alternatively, the grain might be carried deep enough into subduction zone to be completely recycled into Earth's mantle, its crystal structure destroyed, and its constituent atoms incorporated into the vast convection systems that drive plate tectonics. From there, it might eventually rise again as part of a mantle plume, contributing to the formation of volcanic islands in the deep ocean, its silicon and oxygen atoms rearranged into new minerals, new crystals, new expressions of geological creativity. This eternal circulation of materials between Earth's surface and interior ensures that our planet never truly runs down, never becomes geologically dead like Mars or the Moon. The heat engine that drives volcanism, powered by radioactive decay in Earth's core and the gradual cooling of our planet's interior, keeps the rock cycle operating, keeps the continents moving, keeps new land being created while old land is destroyed and recycled. The atmosphere itself participates in these grand cycles through the volcanic processes we have explored together. The carbon dioxide that you exhale with each breath might have been released from a volcano anywhere on Earth, carrying with it carbon atoms that once were part of limestone formations on ancient seafloors, compressed and heated in subduction zones, then returned to the atmosphere through volcanic outgassing. The water vapor in the clouds above your head might have last seen the surface of Earth when it was locked in the crystal structure of oceanic rocks, later released during volcanic eruptions to eventually fall as rain and begin new journeys through rivers and groundwater systems. Even the oxygen you breathe connects to volcanic cycles through pathways that span geological time. Much of Earth's atmospheric oxygen was originally produced by photosynthetic organisms that lived billions of years ago, but volcanic processes help regulate the long-term balance between oxygen production and consumption. When organic materials are buried in sediments and eventually subducted, they remove oxygen from the atmospheric system. When these same materials are later heated and released through volcanic degassing, they can either consume oxygen through oxidation reactions or contribute to new biological productivity through the nutrients they provide. The continents themselves rise and fall in response to volcanic processes operating over millions of years. Mountain ranges built by volcanic activity gradually erode, their materials carried to the oceans where they become the raw materials for future mountain building. The Appalachian Mountains of eastern North America, now worn down to gentle ridges covered in forests, were once as tall and rugged as the Himalayas, built by volcanic processes that operated when the supercontinent Pangaea was still forming.
But these same mountains contain within their worn peaks the roots of ancient volcanic systems. Intrusions of granite and other igneous rocks that formed in magma chambers deep beneath long-vanished volcanoes. As erosion continues to work on these ancient ranges, it gradually exposes these deep igneous rocks, revealing the frozen hearts of volcanic systems that were active hundreds of millions of years ago, when the first complex life forms were just beginning to explore the possibilities of existence on land. The magnetic field that protects Earth from harmful solar radiation also depends on the heat engine that drives volcanic activity. The molten iron core that generates our planet's magnetic field stays liquid because of the heat released by radioactive decay and the gradual cooling of Earth's interior, the same sources of energy that power volcanic activity. Without volcanism and the underlying heat sources that drive it, Earth's magnetic field would gradually weaken and disappear, leaving our planet's surface exposed to the solar wind and cosmic radiation that would make complex life much more difficult to maintain. Climate change over geological timescales also reflects the long-term balance between volcanic outgassing and the removal of greenhouse gases through weathering and sedimentation. Ice ages and greenhouse periods in Earth's past correlate with changes in volcanic activity, continental configuration, and the efficiency of various processes that remove carbon dioxide from the atmosphere. The volcanic processes we have explored together are thus not just spectacular displays of Earth's power, but crucial components of the planetary systems that maintain conditions suitable for life. The elements that make up your body have all participated in these grand cycles. The calcium in your bones was likely released from limestone or other carbonate rocks during volcanic processes somewhere in Earth's past. The iron in your blood was probably smelted from iron-bearing minerals in high-temperature volcanic environments. The phosphorus, essential for DNA and cellular energy systems, was concentrated and mobilized by hydrothermal processes associated with volcanism. Even the trace elements your body needs in tiny quantities, zinc, copper, selenium, molybdenum, were likely concentrated by volcanic processes at some point in their long journeys from Earth's interior to your living tissues. The soil in which your food grows owes much of its fertility to volcanic processes operating over geological timescales. Even in regions far from active volcanoes, the nutrients that support plant growth often trace back to volcanic rocks that have been weathered and redistributed by rivers, wind, and glacial activity. The rich agricultural regions of the world, from the pampas of Argentina to the wheat fields of Ukraine to the rice paddies of Southeast Asia, often reflect the geological legacy of ancient volcanic activity that enriched their soils with essential minerals. As you drift toward sleep while contemplating these vast cycles, consider how they offer a profound perspective on the nature of permanence and change in the natural world. From a human perspective, mountains seem eternal, unchanging fixtures of the landscape. But from the perspective of geological time, they are temporary accumulations of material in constant flux, rising from the collision of tectonic plates, growing through volcanic activity, then gradually returning their substance to the sea through erosion, only to be lifted up again as new mountains in future geological ages. This perspective can be deeply comforting as you face the changes and uncertainties of human life. The anxiety you might feel about transitions and transformations in your personal experience reflects the same fundamental processes that drive all of nature. The constant dance between stability and change, between destruction and creation, between endings and beginnings. The volcanic processes we have explored together teach us that apparent destruction often provides the raw materials for new forms of beauty and abundance. The limestone cliffs that frame scenic coastlines were once the shells of ancient sea creatures. The granite peaks of mountain ranges were once molten rock flowing in underground chambers. The fertile valleys where communities flourish were often carved by the erosional forces that wore down ancient mountain ranges. Every landscape tells a story of transformation, of how apparent endings become new beginnings, of how the permanent and the temporary exist in constant dialogue.
In the deepest sense, volcanism represents Earth's way of staying young. While other planets in our solar system have grown geologically quiet, their surfaces frozen into unchanging patterns that have persisted for billions of years, Earth remains dynamic and alive, constantly reinventing itself through the volcanic processes that bring deep materials to the surface and recycle surface materials back to the depths. This geological vitality creates the conditions that make our planet hospitable to life and ensures that new opportunities for biological innovation continue to emerge over geological time. The rhythms of volcanic activity also teach us about the importance of patience and persistence in natural systems. The most spectacular volcanic eruptions represent the culmination of processes that unfold over decades, centuries, or millennia. The Hawaiian Islands, among the most beautiful landscapes on Earth, took millions of years to build, grain by grain, lava flow by lava flow, through the patient work of deep earth forces that never hurried but never stopped. Similarly, the soil that supports forests and grasslands develops over thousands of years through the slow weathering of volcanic rocks and the gradual accumulation of organic matter. The ore deposits that provide metals essential for human civilization formed through hydrothermal processes that operated for thousands or millions of years, concentrating valuable elements grain by grain in underground environments we are only beginning to understand. As our journey through the science of volcanoes reaches its gentle conclusion, rest in the knowledge that you are part of these grand cycles, that the atoms in your body have participated in countless transformations over the 4.6 billion years of Earth's history, and that they will continue to participate in new cycles long after your individual consciousness has merged back into the vast creativity of the cosmos. The volcanic processes we have explored together, from the sleeping giants in deep chambers to the islands rising from ocean depths, from the language of trembling earth to the ancient song of the ring of fire, continue their patient work while you sleep, gradually reshaping continents, building new mountains, creating new soils, releasing new gases into the atmosphere, and maintaining the delicate balances that keep Earth hospitable to life. In your dreams tonight, you might hear the distant rumble of subduction zones processing oceanic crust, the gentle hiss of hot springs releasing volcanic gases, the quiet crystallization of minerals in cooling magma chambers, the slow creak of continents adjusting to the forces that move them across Earth's surface. These are the lullabies of a living planet, the gentle sounds of a world that never stops creating itself anew. Sleep peacefully in the embrace of these eternal cycles, knowing that you rest on a world that has been billions of years in the making, that continues to evolve and change and create new possibilities with each passing moment, and that holds within its fiery heart the same creative forces that brought forth life itself, and continue to nurture and sustain it through time scales that stretch from this moment of drowsy contemplation to the distant future when our sun becomes a red giant and Earth's story enters new chapters we cannot yet imagine. The volcanic processes we have explored together, from the sleeping giants in deep chambers to the islands rising from ocean depths, from the language of trembling earth to the ancient song of the ring of fire, continue their patient work while you sleep, gradually reshaping continents, building new mountains, creating new soils, releasing new gases into the atmosphere, and maintaining the delicate balances that keep Earth hospitable to life. In your dreams tonight, you might hear the distant rumble of subduction zones processing oceanic crust, the gentle hiss of hot springs releasing volcanic gases, the quiet crystallization of minerals in cooling magma chambers, the slow creak of continents adjusting to the forces that move them across Earth's surface. These are the lullabies of a living planet, the gentle sounds of a world that never stops creating itself anew. Sleep peacefully in the embrace of these eternal cycles, knowing that you rest on a world that has been billions of years in the making, that continues to evolve and change and create new possibilities with each passing moment, and that holds within its fiery heart the same creative forces that brought forth life itself, and continue to nurture and sustain it through time scales that stretch from this moment of drowsy contemplation to the distant future when our sun becomes a red giant and Earth's story enters new chapters we cannot yet imagine.
The volcanic processes that seem so remote from your daily life are actually intimate participants in every breath you take, every bite of food you eat, every drop of water you drink. They connect you to the deep interior of our planet, to the cosmic processes that formed the elements in your body, to the future landscapes that will emerge from today's volcanic activity, and to the eternal dance of creation and renewal that keeps our remarkable planet geologically alive and eternally young. Rest now in Earth's eternal embrace, carried gently toward sleep by the knowledge that you are part of something infinitely larger and more beautiful than any individual human life, yet intimately connected to the volcanic heart that beats steadily in the depths, ensuring that the story of Earth continues to unfold in new and wonderful ways with each passing day, each passing year, each passing eon, in the magnificent symphony of stone and sky, fire and water, destruction and creation that we call home.